All right, guys. So on the last page, we talked about other clustering methods and just some different ideas. What I want to show you now is I want to show you how to select the optimal number of clusters. This is a hard problem. This is an open problem in statistics. It's the reason we have to talk about cross-validation and the gap statistic as you move into this, or cross-validation and bootstrapping. What we're going to do is we're going to use something called the gap statistic. And it leverages the two ideas of cross-validation and bootstrap. So what we want to do is compare some metric from our clustering to some reference distribution or metric to see if there is a difference. That's what this is. This is what you're used to with randomization testing and cross-validation. The question is, how do we do it? Now, we know there are ways to measure the tightness in the grouping of the clusters. So residual sum of squares, within cluster sum of squares, within cluster distance. So how we go about this is a big deal. Now, the gap statistic calculates the difference between the clustering metric on the full data given a specific number of clusters and the same metric from some data generated from the distribution. So basically what you're going to do is you're going to say, imagine there are 3 clusters on my data. And then imagine there's this randomized data that it's all mixed up, there's really no clusters in it, and we assumed there were 3 clusters and fit it. How would this look? How would it do? So we know to calculate any metric on the cluster data, but how do we calculate the information from the reference distribution? What we do is we create a bunch of random samples from our data or calculate a bunch of randomized bootstrap samples from the data we have. Basically what you're going to do is you're going to mix your data up and create this null distribution, if you want to talk about it in bootstrap terms. You're going to create a distribution where no clusters would exist, and you're guaranteeing it because you've mixed up the variables so much that it doesn't matter. So how do you do that? Well, you just go in and you randomly sample each variable and mix up the variables. As you mix up each column of your data, as you mix up each variable, what it does is it creates new observations where no clusterings will exist, or if they do exist, it's just by random chance. In your data set, you haven't touched anything. So what you're going to do is you're going to run the clustering algorithm on the randomized data and then calculate some average metric of the clustering. So the average within cluster residual sum of squares if there's no clustering. And then you want to compare the average distance inside of clusters to for each cluster. So we want the maximum gap statistic. And the gap statistic is the difference between that randomized distribution and the actual clustering you have. When that's large, what it tells you is you got the best clustering possible. Okay? Now notice, when you fit that other clustering, you're still fitting it with the same number of observations. So as this goes and as this looks, what's going to happen is you're going to start to hit this lull. You're going to hit this kind of flat spot. Once you've achieved that flat spot, wherever it's at, you don't do anything else. But what you're going to see is you're going to see what the gap statistic looks like. So to think about the gap statistic, just a quick summary of it. It says, take your clustering with as many clusters as you specified and compare it to something that has no clusters in it, but you tried to force the clusters on it anyway. What's the difference? When that's at its maximum, when that difference is at its maximum, that's the number of clusters you want. Now, so we're going to look at some data that's separated nicely. What it does is it's going to have 3 dimensions, and you're going to try and impose 4 clusters. So there's 3 variables. You're going to have 4 clusters. So that's what I'm doing right here. Okay? And to do this, what we're going to come out and do, there's 4 clusters, one with a mean of 0, one with a mean of 1, 2, 3 standard deviations of each of the data sets, and each of them have 150 data points. So what this is 600 observations in 3 columns, and they just form basically little data clouds. Okay? If you want to, you can try and plot this. I don't suggest it since it is 3 dimensions. If you wanted to drop this down to 2 dimensions, you really could. Wouldn't be a big deal. There's 75 in each of these. There's 50 in each. Sorry. There's going to be 200 observations. There's going to be 50 in each because we have 3 columns. So 150 divided by 3 means 50 observations in each cluster. So not 600, you have 200. 50 observations in each. So each one of the 3 columns is generated from this distribution. So you're going to see what it comes out to be. Now, what we're going to do is we're going to use the clus_gap function. Clus_gap says take X. The function you're going to use is k-means. You're going to use 20 random starts, the maximum number of clusters you have, and you're going to use 60 of these randomized samples. So remember, you force the data on 60 random samples to see what that average is. So you take the average of the bootstrap and look at the difference between what you've actually come up with. So you're going to do 20 starts on each of these and take it. So it takes a minute to run. The clustgap is in the cluster library. So X is the data set I want to look at. Here's the function I'm using. Here's my nstart. And what it comes out with is it says, here's my gap statistic, and here's what this looks like. But if you look at it, we just want the maximum. So we're just going to plot it. We're going to plot it. So what it says is the maximum gap statistic is at 4. That's the biggest difference between what happens if you look at the difference between the one and the other. And you see it starts to come down. Now, what you do is you go back and you refit the data with 4 clusters. It picked what we thought it should, right? That's exactly what we want to happen. Now, what happens if we take that same data and look at hierarchical clustering? Well, take a look at how I defined the clustering method here. So it said function k-means, right? Another way to do this is to use the gap statistic, and this works very, very well with hierarchical clustering. So we're going to use the gap. We're going to say X. We're going to use 8 clusters, 60 60 bootstrap samples, and the clustering method we're going to use is hclust. Now, when I take a look at this, take a look at what I get back. It still says 4 is the maximum, right? So if I plot it, it says 4 is the number of maximum. So what we're going to use is, on the USA arrest, we're going to do it again. So we figured out how to use it for hclust. We figured out how to use it for clustgap. Now let's look at it on the USA arrest data. Let's apply it to something real here. So if we use clustgap with k-means, 20 warm starts, maximum number of clusters is 20. We're going to do 60 bootstrap samples. Now take a look at what happens. What do you see? You see it keep going up and up. First spot it decreases is what? Here's 10, 9, 8. At 8, it hits a local maximum, decreases. 9 hits another local maximum, comes down. Get local maximums and increases again until you're up here around 16, and then you're down again and never come out above 20. So what you're seeing is how this looks. But what's it look like if we run it out to 35 clusters? Let's see if we've actually hit a true maximum. Look at how it continually increases, right? Look at how it continually increases. So what I would look at you guys and say is, look, you've got to try and choose. There's a trade-off here. The more number of clusters you have, the less grouping you're going to have. So what I would do is I would look at something down here and say, okay, there is a maximum amount of clusters I'm willing to interpret. That maximum number may be 10 or 15. And you come in here and say, okay, let's say if there's 10. Well, I'd use the local at 8, right? If I use the local at 8, that gives me an interpretable number of clusters. How does that go? All right. So let's say we max out at 15. Well, the maximum we see is 15, right? If you look at 15 itself, that would be the largest cluster we have. So we would find the maximum inside of 15 and go from there. From our perspective, it's here. But when you don't see it kind of converge like this, what you're saying is, okay, does this actually fit? But this is how you want to select the number of clusters. This is how you want to go about looking at it. So when we look at these things from like the USA arrest point of view, we've done k-means to select it. But what it's telling me is k-means might not fit the data well. So what you can do is you can go back and you can look at, okay, what's it mean if we do this with hclust? All right, how does it look if we do the gap statistic or the gap function using hclust? What does that look like? So when you're looking at these things, you're looking at this for some insight, and then once you select the number of clusters, pick the number of clusters and go in and take a deeper look, okay? Go in and take a deeper look, because when you go in and take that deeper look, what you're going to see is, okay, what do these clusters actually mean? How are they interpretable, all right? So you can see before with USA arrest, we had kind of stopped at 3, but it looks like there's this entire space up here where you'd be better off. At least 8 is where you start to get your minimum up here, right? These bars are standard errors. It shows you how much overlap you actually had on each. You know, from my perspective, they're not as useful in this case, but that's also an indicator that maybe k-means isn't the best choice. So, all right, guys, let me know if you have any questions or need anything.